everyone, my name is Kang. I'm a software engineer on the search team at Wayfair. We're an e-commerce site that sells millions of things for your home online. And today I'm going to talk about how you can bootstrap your own visual search engine. So what do I mean when I say visual search engine? Well, really simply, it's something that takes in some query image and returns similar looking results. And what do I mean when I say visual similarity? Well, there's kind of two different ways you can think about it. There's perceptual visual similarity. And this basically encodes kind of the structure of the image. So you can imagine if you show these two images to an alien, then without knowing what a human actually looks like, they could tell that both of these images are similar. If you kind of lay the images on top of each other, a lot of the pixels line up. Whereas the other one is called content-based similarity. This is more interesting, and it's going to be the focus of my talk today. And this is really understanding what's inside the image. So if you showed someone these two images, they kind of had to understand what animals look like, what a fox is, that one fox is sleeping, but that the underlying content between both images are actually similar. So this is what I'm going to talk about today. Don't bother trying to read the flowchart right now. I'm going to go over it at the end. But basically, the talk is split into two parts. One is training a model to determine content-based similarity. And the other is actually how we're going to use this model to deploy a lightweight image search engine. So let's start with how we're going to train a model. We need a way to represent something as abstract as content-based similarity. We're going to do this with something that we call a latent space. So in this space, we want to be able to take any image and represent it as a point or a vector, or we call it a latent embedding. And when we have images that contain similar things, we want those images to be nearby in this latent space. And when images have dissimilar things, then we want them to be located far apart. So by virtue of having our space constructed this way, this means that if we get some input image that plots somewhere inside this latent space, then finding similar images is just a k-nearest neighbor search in that latent space. So we need something to map our images to embeddings. We're going to define a function that takes in an image, which is just an RGB matrix, and it's going to map it to a 1/n matrix, or our latent embedding. And you might have already guessed, because we're working with images, the way we're going to do this is by training a convolutional neural network. So what's a convolutional neural network? I'm not going to go too deep into this because there are literally like 10 other talks about it here. But this is what one can look like. You can kind of think of it as a directed weighted graph, and an image is fed through one side. It goes through layers of computations, and then you can get some output that you optimize for some task. It's the state of the art in computer vision right now. It's used for things like image classification, object detection, and image captioning. And it's reached human levels of accuracy in some of these tasks. So these things have millions of trainable parameters or weights, which means that they take a lot of time and data to train. You can think on the orders of millions of images and weeks to figure out how to tune all these millions of learnable parameters. Although I'll talk a little bit later about how we can actually speed this up a lot. So like any machine learning problem, we need to gather training data. And this training data is actually going to be pretty simple. First, it's going to be what we call positive pairs. And these are two images that we want the network to embed nearby in that latent space. For us, this was just different images of the same item that we sell. And then we have something we call negative pairs. And these are two images that we want the model to embed far apart. And we just used 2 images of 2 different items, and we randomly sampled those. So we also need to define what our model wants to do with this training data. And this usually takes form of what we call a loss function. So don't try to read this equation right now, because I'm also going to tell you what each part means. But basically, when the model sees one of our positive pairs, let's assume the model currently embeds them into these locations in the latent space. So for our positive pairs, we have a variable y label, and it'll be equal to 1. So if you look back up at that loss function on the top, just take my word that once one of these add-ins cancels out, and then you're left with just this part. So the loss basically simplifies to y label times y disk squared, which is just y disk squared. And the goal of the model is to minimize this loss. So y disk is the distance between those 2 embeddings, those 2 points. So to decrease the loss, the model is going to try to push those 2 points together. And for our negative pairs, let's say the model currently plots both of them in these 2 locations. So for here, y label is equal to 0. So if you look back up at the loss function, then the other add-in cancels out, and now you're left with this side. This side is it basically simplifies to the max of 0, or the difference of margin and y distance all squared. So to kind of help you understand what this means visually, pretend that you draw a circle of radius margin. Oh, and I forgot to mention, margin is some constant number that you choose. So pretend that you draw a circle of radius margin around one of those latent embeddings, those points. The goal of the model is just to push those 2 points outside of each other's margins. Because once you're outside of that margin, then the difference of margin minus y disk is negative, but the max of 0 and some negative number is just 0. And in academia, we call this contrastive loss. So you guys have probably heard a lot about Keras as well during this conference. It's awesome, use it. It is a high-level deep learning package. And we're going to use it to implement something we call a Siamese network. It's called this because it's going to take in 2 images as input and then try to minimize that loss function. We're also going to do something called transfer learning. And this is when we use an existing model with pre-trained weights that is trained on another task. So if you follow computer vision at all, then you probably know what ImageNet is. It's a set of 1.3 million labeled images that span 1,000 different classes. So there's actually a lot of publicly available models that you can get from Keras or TensorFlow that are trained on doing classification on these images. And the reason why we want to do transfer learning is because all these models generally learn how to perceive images and lines and the shapes in them. So if we start off with another model and we just train on top of it, then we're already at a good starting point. So this actually can help you speed up training from a matter of weeks from scratch to a matter of hours. And we also need a lot less data. So instead of needing millions of images, we might only need thousands. And this is because when we do transfer learning, the model essentially has already looked at millions of images. So we're just going to kind of fine tune it on our domain set. And I'm not really going to go into how we implemented this or walk through all the code, because there's not enough time for that. But we made a Jupyter notebook with a Docker image that you can use that actually walks you through how to train the Siamese network if you just provide your own images. So let's assume that you trained a model and it evaluates well with your evaluation test set. And you want to deploy it to be used in real time. So we're going to want to deploy this to a microservice. One of the first things that we need to do is to index all these images into that latent space. So we're going to take all the images that we care about, that we want searchable, and we're going to take that Keras model that we just trained in the other slide. And we're going to feed our images through that model and essentially get a list of image embeddings. And this is all within that latent space. And we're going to want to do, so I mentioned before that to find similar images, you can just do a k-nearest neighbor search. So you could do that brute force, but that's obviously really slow. And if you're doing image search in real time, then you want that to be fast. So there's a lot of packages and libraries out there that allow you to create these efficient data structures that let you search, that lets you do KNN searches really quickly. So one of the first steps is to just pick one of those libraries. I'm just using sklearn's ball tree implementation here because it's really simple to show on slides. And then you're going to, and this is some pseudocode, take all of your images and feed them through the network and get their embeddings. And then you'll have a list of image embeddings. Then you're going to create this ball tree object, this KNN index structure with those list of embeddings. And we're going to pickle it or serialize it and save it for later. So we're going to put that to the side. The next thing that we want to do is actually to make our Keras model usable in real time. So you might think that you can just import Keras into Python and load your model up, but depending on how you deploy this, if you don't want to deal with forking TensorFlow sessions, which is terrible, then you'll want to use something called TensorFlow serving. And I forgot to mention that Keras actually runs TensorFlow as its backend. So Keras is just, well, it runs TensorFlow as its backend by default, and Keras just calls functions in TensorFlow. So there's something called TensorFlow serving. It is a high-performance gRCP service that lets you host TensorFlow models. It's written in C++, and it has CUDA and CPU instruction support, which helps you speed up your models a lot. And all we have to do to use TensorFlow serving is to export our Keras model as a save model file. And that's just a few to do that is just a few function calls in Python. And then once you start TensorFlow serving, you just say load up this save model file, and then TensorFlow serving will be running with your model that you trained in Keras. So this is a snippet of code assuming that you have TensorFlow serving running on how to actually access your model. The first thing that you're going to do is just to create a connection object to your TensorFlow serving host. Then you're going to create a request object. So this is just specifying which model you want to access in TensorFlow serving, because TensorFlow serving actually allows you to load multiple models. So here we're just specifying the model name and something we call the model signature. Then you want to set your model's input, and the input to our model is just going to be an image. And you send that request down to TensorFlow serving, then you get back a request where you can pull out the embedding from your model. So now that we have a way to search our images really quickly with that KNN search structure, and now that we have a way to embed our images in real time, we can use Flask to kind of integrate the two together. So this is a really simple Flask application. And the first thing that it does is it just loads that pickle that we made before, that ball tree, so that we can do KNN search within our latent space. And then you want to create an endpoint that allows clients to post images over. And when you get those images, you can use TensorFlow serving to get those embeddings, get the embeddings for those images. Then once you have the embedding from TensorFlow serving, you just use the ball tree, the KNN structure, to do the search within your space. And you get back the image IDs, and then you format your response however your client expects, and the client can do all the front-endy stuff and render images and such. So just to go over really quickly everything I talked about again. First thing, we want to start with training, and we're going to use Keras. And to train with Keras, we're going to get all of our own images and train that Siamese network. In the end, we're going to have this trained Keras model. We're going to use this model to embed all of our images and get those latent embeddings. And then we're going to make that, that KNN search structure and pickle it to memory, to pickle it to disk. We're also going to export that trained Keras model as a saved model file, which is going to allow us to load it up into TensorFlow serving. And once you have that, we can start making the microservice. And we're just going to start up a TensorFlow serving host and tell it to load up that saved model file. We're going to start up a Flask application and load up the ball tree pickle when it starts up. And Flask and TensorFlow serving can talk to each other. So when Flask gets an incoming image, it can go to TensorFlow serving, embed the image, and then use that embedding to do a KNN search in memory. So there's a few, so what I described is really simple, and there's a few tweaks that you can do to kind of improve this, this architecture. One is actually on the training side, and it's using something we call triplet loss instead of the positive and negative pairs. And basically, instead of showing the network 2 images at once, you're showing the network 3 images at once, 2 similar images, and 1 dissimilar image. And people in academia have found that this actually helps a lot with model accuracy, although it matters a lot how you pick your triplets. So you can actually decrease your accuracy if you pick your triplets not well. Another thing that we can do is actually shard out that KNN structure that I showed you before, the ball tree. In the slides before, I just had one giant ball tree which you're going to perform all of your KNN search over. But you can actually break apart that data structure and then at query time use some logic to selectively only search some of your ball trees. And this reduces the search space a lot and allows you to speed up your queries a lot. And we can also do the KNN search in something like Celery. This is really nice because Flask becomes completely I/O bound at that point. And then you have these Celery nodes which are doing all the KNN searches and they're compute bound. And then you have your TensorFlow serving nodes which are running the model inference and they're also compute bound. And you can scale them all independently depending on where you see you need resources. So how does this scale? I'm going to talk a little bit about how we implement, how well this works at Wayfair. We can embed images in about 50 milliseconds on GPUs. On CPUs, it's about 100 milliseconds. And we can handle about 100 images per second on TensorFlow serving with our model. And this is what's something really cool in TensorFlow serving called batching enabled. And this is basically if you have a bunch of clients that are connecting to TensorFlow serving, what it'll actually do is it'll wait for a batch of incoming requests. And then once some time period expires, it will push that batch all through, it'll feed that batch all through the model at once, which is actually more efficient than feeding the images one by one. And then once it gets the output, it will send each client its respective subset of the end results. So this is also timings on the network architecture that we use, but you could potentially get even faster times if you use a more efficient network architecture for your convolutional neural network. And we have over 10 million image embeddings that we search over in our visual search engine. Our latent embeddings are 256 degrees, and we use 32-bit floats. And we actually don't do a true KNN search. We do an approximate KNN search, which we found improves performance by 4x, as well as not actually degrading the qualitative results that we saw. And this, in total, means that it takes about less than 100 milliseconds to actually, when an image comes into the microservice, to when results come out. So I said that you could bootstrap your own visual search engine, and you can with our Docker images. So basically, I kind of showed you a link to the Jupyter notebook that I had earlier on how to train the Siamese network. And you actually don't even need to train a network to start experimenting with this. This is because we can just use one of those public models. So what the repo will do is grab Google's Inception ResNet v2 model, which is trained on ImageNet for image classification. But if you know a little bit about deep learning, what we're going to do is actually pop off that last classification layer and then use the new final layer as the embedding layer. And that actually works fairly well. It seems like that layer encodes something about the semantics of what's in the image. And yeah, you can just, without any training, you can start using that model and its embeddings as is. But you can also additionally train on top of that repo, or sorry, that model, to really fine-tune the model to work the best in how you believe your users will use it. So if you're building a model to just search dog breeds, then you probably want to train it on like all dogs. And this repo will also allow you to create those fast KNN structures that I talked about. And then for the microservice, this is the Git repo for it. Basically, once you have the save model file and that KNN pickle, you just have to drag them over to this repo into some directories. And because it's all Dockerized, you just do docker compose up, and then you'll have a running visual search engine, which you can play around with and see if this is something that's valuable for you. I also want to note that this is probably not something that you want to use in production. It's more of just, you want to see if something like an image search engine is actually useful for whatever you're trying to do. We also found that it can be useful for things like for recommendations. So as an alternative to collaborative filtering, because collaborative filtering it has the problem of cold start. So if you have a new product without any interaction data, then you can't really get it recommended. But you actually can recommend it if you use visual similarity to say like, hey, you looked at this product. A bunch of these other products look similar. Maybe you're interested in these. And these also come in different price points. So if you like this really expensive thing, but you're kind of cheap, then maybe you want to buy this other thing that looks the same, but costs like 10 times less. So that's my talk. Thank you for listening. I'm open to any questions.
Thank you. Great talk. I was curious if you can shed some light on accuracy numbers and things like that, performance.
Yeah, so we do a couple of accuracy metrics. One is recall rate. So we'll actually create one of like those giant ball trees. And then when we're measuring our model, we will we'll take an image embedding and then search over our space and see if we get back images of the same item. And I don't know if I'm allowed to share like actual numbers, but yeah, it does well. And then we have an additional classification layer that we added, that we kept on the actual model. And this is because we sell many different types of items like chairs, sofas, beds. So we also use a classifier loss to make sure that like the model is understanding what different objects are.
Thank you. That was a great talk. So it sounds like you didn't end up putting this particular thing into production. Can you say anything more about what alternative you might have used or anything?
Yeah, so we actually did. So we put something. So we did put this in production, but what I meant is the code that I shared on our public GitHub is not the same. Yeah. So the one that's on our public GitHub is really simple. It doesn't. It probably won't scale that well if you try to use what we have publicly. But it's really just like an easy way to kind of see how this might work with your data.
Thanks. Yeah, I was wondering if you could share some of your practical experience with triplet loss and how you selected the triplets.
Yeah, so when we trained a model with triplet loss, it did worse. We're still experimenting on how we want to pick those triplets. And so one of the things about our images is we have rich attribution on our images, so we know what color the products are, like what style the product is, so modern and traditional and chic and a bunch of other data about the images. So we're trying to look into how we can use those attributes to better pick our triplets. But yeah, we haven't had good success with it yet.
Hi, I'm wondering if you guys use tags at all to like for example, if you're searching, if it's just image search, or you also use like image plus like text to help.
Our search is explicitly just based on the way that the image. I'm not sure if I quite understand your question. We just use the image itself to do queries.
Okay.
And this is because so the use case is a user will go on their phone and take a photo of a product that they might want to buy. And that wouldn't come with any tags. But so one of the things that we do allow is if the search results don't look good, then you can filter down on like different types of classes. So if you took a picture of a chair, but you got back lamps for some reason, then you can actually say, hey, force a search on chairs.
Yeah, that's the use case I was wondering. Thank you.
Any other questions? Oh.
What's the dimension of your latent space?
It's 256 dimensions.
Do you know of any libraries to do the KNN that maybe save to disk or actually are updatable or can be shared, like more of like a database type of tool?
I don't currently know of a KNN search library that does that. What we do when we want to update our libraries, our objects, is we just recreate the entire object from scratch. And with our, so we only have 10 million images, so that actually works for us. But yeah, I think I've had heard of packages that allow you to do that, but we just haven't explored that.
Is the margin a hyperparameter, tunable hyperparameters?
Yes. So we just keep it to, so we set it to 1 to keep the latent space compressed.
I was wondering when you started with the pre-trained ImageNet, since it's looking for animals and guacamole and all other kind of things besides furniture, I wonder if you tried like dropping multiple of the top layers, or how would that work?
Yeah, so we did try chopping off different parts of the network, but we found the most success in just chopping off the final classification layer. And then we freeze some of the initial layers, which like do the extraction for lines and shapes. And then we train basically up the mid part of the layer.
If there aren't any other questions, I guess, yeah, we have 10 minutes left before 3:20, so there's plenty of time. I guess we can all go, or yeah.